you.
Can you speak?
Hello.
Just double check.
Or
Okay.
okay, so these different formation mechanisms will leave different leftovers of intermediate mass black holes. So studying these objects in the local universe is really important. Is it okay?
Yeah.
All right.
Just if you wanna remove the Zoom things. Yeah, perfect. Thank you.
There you go. Okay. The motivation to use CDF is because we're in the time domain, right? So it is a cheaper tracer of black hole accretion, especially when dealing with large samples, right? In comparison to spectroscopy, for example. Also, CTF delivers long light curve baselines, longer than 5 years. And this is important because it has been shown by Kozlowski that the light curve length should be at least 10 times the expected variability timescale. And by the work of Colin Berg and others, it has been shown that the variability timescale of intermediate mass black holes like NGC 4395, which is the archetypical IMDH, is in the order of days or weeks. So we need long light curve baselines. Also, both CTF and Beta Rubin will deliver or are delivering different imaging. And this is essential to remove the host contamination, so the constant part of the emission of the things that we're observing, because we just want to get the viable part. So my scientific goals are these two: demonstrate the viability or not of using variability as a selection tool of intermediate mass black holes. Also, I would like to correlate or to look at the correlation of the variability features that I am going to find with the physical properties of this sample, such as black hole mass or Eddington rate. Okay, so my sample comes from these main three works. So I have around 1,700 objects. They're located in the northern sky. So these works use STScI spectra to determine the black hole mass with the width of the H alpha line. Here is the redshift distribution in the lower left panel with a median of 0.07, so it's a pretty local sample. And I said partial result because so far I've analyzed 1,400 of these 1,700 objects. So here I'm presenting the black hole mass distribution and the volumetric luminosity distribution as well. So you can see that, as expected, the majority of our objects have larger masses, but it has to be noted that around 15% of our objects have masses lower than 2 × 10⁵, which is the arbitrary limit that people have set so far. I don't care about it too much because I think that all of our sample is important in itself because it's a poorly studied mass regime in black holes. All right. So regarding the methodology, we have developed CPF, which is a pipeline based on the work of Patricia Arevalo 2026 that performs aperture photometry using CTF different images. So it is science images with the reference image subtracted. So the main goal of this pipeline is to mitigate phase variability that we might see due to bad calibration or photometry. And it has been proven, we've seen this, and Patricia also shows that in her work, that is much more accurate than the CTF data release and force photometry server. So she looked at the deviation of the light curves, and you can see that there is an improvement for all of these type of objects. So non-variable stars, a huge improvement on non-variable galaxies or almost an order of magnitude, an improvement for low redshift galaxies, and a mild but still existent improvement for mid redshift AGNs. So we tweaked a little bit this code. Patricia just downloads everything from the field. Now we have improved it so we can ask for information of particular objects given the coordinates. So now we know pre-known positions and we take flux from the different images here. So we also applied a process that can be seen in this left panel, where you can see structure in the noise level across the CCD for this particular object in the top left part, and throughout all the calibration process, that structures are removed. And here in this right panel, you can see an improvement of the noise by a few percent. So we had noise given by the dashed line curve, and then we have an improvement given by the solid curve of a few or even tens of millimagnitude. And this is important because the variability that we want to measure is right about at that level. All right, so for the analysis, we have used statistical metrics, which is the median absolute deviation or MAD. So we want to assess the deviation from the median compared to a set of non-variable objects. Yeah. So this metric asks at each observing time, so each epoch, how unusual is the AGN flux change? So this delta over here compared to a non-variable set of sources at that same exact epoch. So let's take that epoch over there. So we have a delta, we compute the median absolute deviation, then we compute the CMAD value, and we go to the sample of non-variable objects for the same epoch, and we do the same, and we build this comparison set. Then we take the epoch from the AGN and compare it with this population. So we are doing this population-based classification, and we can see that that particular epoch is an outlier. So then, if we take all the epochs, we take averages and medians, we can say if the source is variable, its light curve is variable or not. So that's the metric we are using. Given that epoch, we ask, compared to the non-variable stars or galaxy non-variable sources that we have, in the field, how extreme is the variability of the agent, and we are using a threshold of 95%. In the median of the CMAT, and we require the agent to have more variability than 95% of the comparison set. And given these metrics, we have defined that out of the 1,400 objects so far, we have found 100 that are variable, so about 8% of the sample. Then, for the frequency part of the analysis, we have used the power spectral distribution, which is the Mexican hat power spectra. It's another work developed by Patricia Arevalo in 2021. So basically, what she did here is to take a light curve and then build a Mexican hat filter with two Gaussians, convolving two Gaussians, and see how the light curve responds to that particular frequency of the filter. All right. So in that way, we can know the power that comes at each frequency, and we can build a power spectral distribution. So we obtain PSDs, we fitted power slopes to it, and we want to look both at the slopes and the excess with respect to the noise levels of the PSDs, all right? So here you can see two examples of IMBH candidates in my sample. You can clearly see that they are variable. Of course, I'm showing the best ones. And you can see that it has a clear slope and a clear excess above the noise level, right? Instead, this other source, it has an excess in the low frequency region, but not in the high frequency region. So typically, the conceptual PSD schematics is shown in the left plot here, where you have a saturated level for lower frequencies, and for high frequencies, the power spectra is expected to behave as the frequency to the -2. And we expect for supermassive black holes, it is known that they have values of the power slope between -2 and -1. But for our samples, when we compare the variable and the non-variable part, we can see that we do see a slightly steeper distribution of slopes for the variable subset, but the difference is not that great. So it indicates that there is some variability present, but we are not able to separate these two populations based on the power law slope alone. If we look at the PSD excess, so how much the PSD, the power signal above the noise level is, and we compare it with the mean magnitude of the G band of CTF, we can see that the variable and the non-variable objects face the same population. So we don't see a strong function between the excess of the PSD and the mean magnitude. And also there are a few objects that are bright that are picking up a little bit more noise. And that is why we have these contours over here, because we're comparing to the noise level and not to the calibration object. So it's systematic observational noise. Okay, now if we compare the variability metrics with the physical properties, I am comparing here the percentile of the CMAT value and the CMAT median with black hole mass in the first row and to the Eddington rate in the second row. So you can see from the histograms as well that we can find variability for the complete range of objects in our sample. So we don't find a strong relation between variability and black hole mass in this particular range of masses, at least. On the other hand, we do see that the variable sample traces a slightly higher Eddington ratios compared to the non-variable set of AGMs, which is super interesting. So the fact that we do not see a dependence on mass to the variability might suggest that there's a common driver of variability for all the objects in our sample. So if we compare the same variability metrics, but this time with X-ray detections, and we also compare with mid-infrared colors from WISE, we can see three things. One, that the X-ray detections are present for more luminous sources. compared to the non-variable subset. Two, that across the variable set of AGNs, we have a larger X-ray coverage, so around 20% for the X-rays, and 8% for the non-variable set. And the third thing is that we don't see any dependence on the color, so we don't see any change, presence of maybe like obscured torus or not. But it is interesting and it is important to find more X-ray within our variable set in comparison to the non-variable set of AGNs. We also plotted the PPT diagram. So you have in orange points the variable set, in blue crosses the non-variable set, in red circles the ones that are X-ray detected for the variable ones, and in black circles the ones that are X-ray detected for the non-variable ones. So you can clearly see that, interestingly, we can find a larger fraction of variable sources that are X-ray detected for the low metallicity regime of the VPT diagram. And yeah, this is just, this is new. So we still have to see what are the differences, for instance, in the light curves or the PSDs when comparing these different populations. So I think this is exciting. So yeah, my conclusions here. So basically, we have successfully defined and tested variability metrics that allows us to separate variable from non-variable sources. And there are no dependencies so far, and I don't think there are going to be, between variability when we compare with mass and magnitudes. We do find slightly larger emission ratios linked to variability, and we also can find a larger fraction of cover of X-ray detections for our sources that are variable in comparison to the ones that are not. For the future work, as I said in the past slide, we would like to compare different populations, compare, for instance, the variable X-ray detected versus the X-ray detected but that are classified as non-variables. But there are still a lot of open questions. So we were expecting at the beginning of this project to find a way larger fraction of variable objects, thus confirming the AGN nature of these objects. So why are we only finding 8% of them? So this might be related to the way that we are obtaining the sample in the first place through spectroscopy. How much do we trust the black hole mass there or not? Also, it is interesting to try to understand why, even though we have a larger X-ray detection coverage for the variable subset, why still 80% of them do not show X-ray detections? And what's the relationship of all of this with accreting duration? We don't have clear trends yet. So yeah, thank you very much. Happy to receive any questions.
Great, thank you, Ernesto. Any questions for Ernesto?
Thanks, very interesting talk. One comment and one question. So the question is the method that you were describing where you're using the MAD per epoch is the reason you're doing this per epoch and not more globally that just the seeing conditions and whatever else is okay.
Yeah, it's observing conditions because it depends, it varies a lot. And there's some method that the CTF provides that tells you how different it is, so we rather use it like per epoch.
Okay, yeah, good, makes sense. And then the comment I wanted to offer is just that for X-ray binaries, when we look in the sort of few percent up to around Eddington limit when things are sort of in a soft state, variability is very low. We tend to see the high variability in either very low luminosities or sort of high super Eddington.
Yeah.
So it's possible this is sort of suppressing the signal in that luminosity.
Yeah, it is. Although also like our over limits of X-rays are pretty high, so I would like to look more into that to see maybe we can catch a little bit more of IMBHs and increase the sample or not. But it would be interesting to look at. Thank you.
Any other questions? From Zoom or in the room? Okay, yeah.
I'm a little puzzled because I'm not very familiar. If you go one slide back, why are you plotting this line ratio to see what you look comparing the variability?
These lines.
Yeah, that line ratio. Why that line ratio? That I don't know. I mean, that's why
I mean, we were just trying to look for the position of these objects in the PPT, so if maybe they are shock driven or yeah.
So that shows you that it's shock driven,
So
if it's high.
This region is more like shock driven. This region is more star forming. The ones that are up there in the upper right panel, part of the plot, those are more secure AGNs. And this low luminosity part, it's also interesting because we usually don't expect that many agents to be present there. Yeah, so these different parts of the plot tell you different conditions of the surroundings of the sources that we are looking at, and what the ionization is going around.
Okay. Just one comment on the variability you talked about, that you don't find variability that is depending on the magnitude of the object. But that's also a very standard thing for the X-ray as well, because the variability, RMS, does not depend on the count rate of the object. So it could be very low count rate, but very variable.
Yeah.
In RMS, and you'll find a lot of noise, for example, in the power spectrum, but then it could be extremely bright, no noise or nothing, because there will be no variability, but it will be extremely bright.
Yeah.
So it's the same thing in the X-rays. So I couldn't quite understand, maybe that also question you asked at the end, why you're trying to actually, you find 80% of the AGNs variable in the optical, but then those objects are not detected in the X-rays.
Yeah, so like out of the 100 objects that we define as variable, only 19 of them are X-ray detected. So yeah, the question is like why not like more of them are X-ray detected? Like what's happening there? Is there maybe like a change in the accretion disk that is damping the X-rays?
Those AGNs have ADAPs, right?
Yeah, I mean,
The ADAPs don't radiate.
yeah.
So you may not detect it depending on the state.
Yeah.
It's possible.
Yeah.
That you're not, maybe it's like conditions that you have to, then you probably have a lot of like variables that you have to, parameters that you have to really sort of to understand that answer to that question. So it's not very clear.
I agree. Thank you.
Thanks. Any final questions for Ernesto? Yeah, Igor. Or, yeah.
Comment on the recent point. So we are not in the same regime as an X-ray when you look at the variability, because we have high background. So normally, because of the background, you expect that you detect fewer variable sources at low fluxes. So it's like, imagine if you try to look at X-ray, but not with Chandra, but rather with SMM Newton, where the background is crazy. And the other thing is that here, for the X-ray detectability, we are incomplete in X-ray in terms of coverage, because we can have, like, this is a compilation that the X-ray detection that came from the archive, Chandra or XMM Newton. And later we added some sources from Eurozeta, but Eurozeta is not really deep, and it's only half of the sky. So, and it's the southern half that doesn't really correspond to the coverage of STSS.
Right.
So there might be a lot of selection that plays a role here. So like this 80% non-detection in X-ray doesn't mean that there's no X-ray. Sometimes it means that there's no observations.
Okay. Great, thank you. Any final questions? No, with that, let's thank Ernesto again. We'll see you on Friday at 2:30 p.m. for our final special head seminar.